Hello, friend, and welcome back to Science for Sleep, a calm place where gentle facts drift softly and the world slows just enough for rest to feel natural. Tonight, we'll spend some unhurried time with one of the most familiar and quietly scientific moments on Earth, the slow coloring of the sky as day leans into evening. The sun itself remains steady and unchanged, yet its light appears to soften, warm, and deepen as it sinks toward the horizon. Sunsets often feel poetic or emotional, but beneath their beauty lies a calm, understandable process shaped by light, air, and motion, unfolding patiently whether anyone is watching or not. At its simplest, a sunset happens because sunlight must travel through more of Earth's atmosphere when the sun sits low on the horizon. During the middle of the day, sunlight passes almost straight down through the air, but as evening approaches, that light begins to skim the atmosphere at a shallow angle, stretching its journey across a much longer path. Along the way, the air itself gently reshapes what reaches our eyes, not by effort or intention, but through ordinary interactions between light and tiny particles suspended all around us. Sunlight may look white when it shines overhead, but it is actually made of many colors blended together, each carried by its own wavelength. As this light moves through the atmosphere, shorter wavelengths scatter more easily, while longer wavelengths continue forward with greater ease. This quiet sorting process happens constantly, without sound or motion, and becomes most visible when the sun sinks low enough for its light to be filtered and softened by distance. There's nothing you need to remember here, and nothing to figure out. These ideas can simply rest in the background, like distant scenery passing by a train window. The science of sunsets isn't something to solve, only something to notice, allowing the sky to do what it has always done, long before names or explanations existed. If you enjoy these quiet journeys, I invite you to subscribe, and if you feel comfortable, to leave a comment sharing where you're listening from tonight. It helps others find their way to this calm corner of the world, one sleepy traveler at a time. For now, you can let the pace slow even further, allowing your thoughts to loosen as the light of the day continues its gentle fade. As we settle into this long, unhurried exploration, you can let your mind wander without direction, knowing that the sky follows the same patterns each evening, guided by simple physics and patient time. We'll stay with that calm rhythm together, letting the science unfold softly, one color at a time. I'm glad you're here. Long before the sky begins to change color, long before evening becomes visible at all, light is already on its way toward Earth, moving quietly through space without warmth or sound. Sunlight begins deep within the sun itself, where energy is released and slowly makes its way outward, eventually escaping as a steady stream of electromagnetic waves. By the time that light reaches Earth, it has traveled nearly 150 million kilometers, arriving evenly and patiently, carrying no preference for morning or night. What we casually call sunlight is actually a wide range of wavelengths bundled together into what appears to human vision as white light. Within this blend are all the colors the human eye can detect, from violet and blue at the shorter end, through greens and yellows, and into orange and red at the longer end. These colors are not created by the atmosphere or the sky, but already exist within the light itself, waiting only to be separated or revealed by the conditions it passes through. Each wavelength of light behaves slightly differently as it moves. Shorter wavelengths tend to interact more easily with small particles, changing direction with little effort, while longer wavelengths are more resistant to being scattered, continuing forward in steadier lines. This difference is not dramatic or sudden, but subtle and constant, governed by simple physical relationships between energy, wavelength, and matter. Nothing in this process is rushed, and nothing is lost, only redirected. Human vision adds another gentle layer to this story. Our eyes are tuned to a narrow slice of the full electromagnetic spectrum, sensitive only to what falls between certain wavelengths. When all of those visible wavelengths arrive together, our brain interprets the blend as white or pale yellow light, depending on its intensity and angle. Color, then, is not just a property of light itself, but also a quiet collaboration between physics and perception. As sunlight moves toward Earth, it does not arrive in isolated beams or separate colors. It arrives as a unified flow, consistent and predictable, shaped by physical laws that do not change from one evening to the next. The variations we notice later, the deepening hues and shifting tones, emerge only because this light encounters an atmosphere filled with gas molecules, moisture, and motion, each gently nudging it along a slightly altered path. You don't need to hold on to these details or sort them into memory. They can simply exist in the background, like a low hum beneath awareness. Light travels, wavelengths differ, and perception completes the picture, all without effort or attention. Even now, as daylight continues its slow descent somewhere beyond your walls, the same calm processes are unfolding, steady and unbroken, just as they always have. For much of the day, the sky holds a steady shade of blue, a color so familiar that it often feels permanent, as though it belongs to the sky itself. Yet this color is not a surface, nor a layer stretched above the earth. It is the visible result of countless tiny interactions taking place high overhead, where sunlight meets the thin, nearly invisible mixture of gases that surround the planet. As sunlight enters Earth's atmosphere, it encounters molecules of nitrogen and oxygen, each far smaller than the wavelengths of visible light. These molecules do not absorb sunlight in any meaningful way, but they do scatter it, gently redirecting light in many directions. This scattering does not affect all colors equally. Shorter wavelengths, particularly those associated with blue and violet light, are scattered far more efficiently than longer wavelengths such as red and orange. This process, known as Rayleigh scattering, occurs continuously anywhere sunlight passes through a clear atmosphere. Although violet light scatters even more strongly than blue, it contributes less to the color we perceive. Human vision is less sensitive to violet wavelengths, and some of that light is absorbed by higher layers of the atmosphere before it ever reaches the ground. What remains, dispersed across the sky in every direction, is predominantly blue light, arriving from all angles rather than directly from the sun. This is why the sky appears blue even when you look away from the sun itself. When the sun is high overhead, its light takes the shortest possible path through the atmosphere. There is less distance for scattering to remove significant portions of the visible spectrum from the direct beam of sunlight. As a result, the sun still appears bright and pale, while the scattered blue light fills the surrounding sky evenly. The balance between scattered light and direct light remains relatively stable throughout the middle hours of the day. This steady blue sky is not a separate phenomenon from the colors that appear later in the evening. It is part of the same ongoing process, quietly preparing the conditions for sunset long before the first warm tones appear. Each moment that sunlight travels through the atmosphere, a portion of its shorter wavelengths is gently redirected, thinning the light that continues forward in a straight line. Nothing dramatic happens when day begins to turn toward evening. The same scattering continues, unchanged in its rules or behavior. Only the angle of the sun slowly shifts, lengthening the path its light must travel. What feels like a transformation later on is simply the cumulative effect of distance and time, revealing what has been happening all along. You don't need to picture the molecules or follow their motion. They move without effort, responding only to physical laws that never hurry. The blue sky above you is the quiet evidence of that patience, repeating itself each clear day, waiting calmly for the sun to lower, so that different colors may finally remain behind. As the day continues its slow passage, the most important change taking place is not in the light itself, but in the position of its source. The sun does not suddenly dim or alter its output as evening approaches. Instead, Earth's steady rotation gradually lowers the sun's apparent position in the sky, changing the angle at which its light reaches the surface. This shift is subtle and constant, unfolding so gradually that it often goes unnoticed until the colors begin to change. When the sun is high overhead, sunlight enters the atmosphere along a relatively short and direct path. As the sun moves closer to the horizon, that path lengthens. The light must now travel through a much greater thickness of air before reaching the ground, passing sideways through layers of gas that it previously crossed almost straight through. This extended journey is the single most important physical reason sunsets exist. The atmosphere is not a solid boundary, but a deep, layered envelope that becomes denser closer to Earth's surface. As sunlight travels at a lower angle, it encounters far more air molecules, dust particles, and tiny droplets of moisture along the way. Each interaction gently redirects some portion of the light, gradually reshaping the balance of wavelengths that remain in the direct beam by the time it reaches an observer. Shorter wavelengths, especially blue and violet, are scattered away more efficiently as the path length increases. With more opportunities for scattering, less of this shorter wavelength light continues forward in a straight line. What remains is light dominated by longer wavelengths, which are less easily redirected and therefore survive the extended journey more intact. This gradual filtering process happens continuously, not suddenly, allowing color to deepen slowly rather than appear all at once. The sun itself also begins to change in appearance during this time. As more blue light is scattered out of the direct path, the remaining light reaching your eyes becomes warmer in tone. The sun may appear yellow, then orange, and eventually red, not because its surface has changed, but because much of its original spectrum has been gently removed along the way. The sky near the horizon follows the same rules. Glowing with the colors that remain after scattering has done its quiet work. This process depends only on geometry and distance. There is no switch that turns evening on, and no boundary where day abruptly ends. The colors of sunset emerge because the sun's light is being viewed through a longer slice of atmosphere, allowing familiar physical laws to express themselves more visibly. What feels like a moment of transition is actually a gradual accumulation of tiny effects. You don't need to follow the sun's motion or imagine its path. Earth turns steadily beneath it, carrying the horizon upward as the light continues forward. The atmosphere responds as it always does, scattering, softening, and reshaping what arrives. Even now, as the sun lowers somewhere beyond view, this same patient geometry is unfolding, guiding daylight gently toward its evening tones. As the sun settles closer to the horizon, the change unfolding is quiet but profound. Light that once arrived almost straight down now glides sideways through the atmosphere, tracing a longer, more winding route before it reaches the ground. This extended journey does not alter the light's origin or energy, but it greatly increases the number of encounters it has along the way, allowing subtle effects to accumulate with patience rather than force. The atmosphere grows denser nearer Earth's surface, not abruptly, but gradually, layer by layer. When sunlight approaches at a low angle, it passes through these thicker layers for a longer distance, meeting far more air molecules than it did earlier in the day. Each encounter gently redirects a small portion of the light, not enough to be noticed on its own, but enough to matter when repeated thousands of times across a stretched path. Because scattering depends on both wavelength and opportunity, this longer path makes a visible difference. Shorter wavelengths are given more chances to be scattered away from the direct line of sight, while longer wavelengths continue forward with greater persistence. The process is the same as it was at midday, governed by the same physical rules, but the geometry now favors gradual filtering rather than balance. This filtering does not happen all at once, and it does not affect the sky evenly. Light traveling toward the horizon experiences the longest atmospheric path, while light higher above still moves through thinner layers. As a result, color changes often appear first near the horizon, deepening slowly upward as the sun continues to descend. The sky becomes a gentle gradient rather than a uniform field, shaped by distance rather than intention. Tiny variations in atmospheric conditions can subtly influence this journey. Slight changes in air density, temperature, or moisture content alter how light is scattered, even when the sky appears clear. These differences help explain why sunsets rarely repeat themselves exactly, even though the underlying physics remains constant. The atmosphere is stable, but never perfectly uniform, allowing small variations to leave quiet signatures in color and tone. Nothing about this longer journey requires effort or direction. Light does not slow itself or choose its path. It simply continues forward, responding naturally to the environment it moves through. The atmosphere does not act as a barrier, but as a soft filter, reshaping light through countless gentle interactions that occur without sound or motion. You don't need to picture this path in detail. It is enough to know that as evening approaches, light spends more time within the air that surrounds the planet, and time allows small effects to become visible. The colors that will soon emerge are not created suddenly, but prepared gradually, carried forward by distance, patience, and the steady turning of Earth beneath the sky. As the sun continues its slow descent, something subtle begins to happen within the light that reaches your eyes. The familiar blues that once filled the sky so completely do not vanish, and they are not destroyed. Instead, they are gently redirected, scattered away from the narrow path that leads straight from the sun to the horizon. Their journey simply changes direction, becoming more diffuse, more spread out, and less concentrated in any single place. Blue light belongs to the shorter wavelengths of the visible spectrum, and these wavelengths are especially sensitive to interaction with the atmosphere. As sunlight travels through its lengthened path near the horizon, blue light encounters countless air molecules and tiny particles. Each interaction nudges it slightly off course, sending it outward in many directions rather than allowing it to continue forward in a straight line. Over distance, these tiny deflections accumulate, thinning blue light from the direct beam that reaches the ground. This scattered blue light does not disappear from the sky. It becomes part of the broader atmospheric glow, diffused across wide angles and often rising higher above the horizon. While the direct sunlight grows warmer in color, traces of blue can still be found overhead, lingering softly as the contrast between sky and horizon slowly increases. The sky becomes layered, not because colors are being added, but because some are being gently redistributed. Violet light follows a similar path, scattering even more readily than blue. However, its influence remains subtle. Human vision is less responsive to violet wavelengths, and some of that light is absorbed or redirected before it ever reaches the surface. What remains visible to us is the gradual quieting of cooler tones within the direct light, rather than their complete absence from the sky. This process unfolds continuously and without interruption. There is no precise moment when blue light leaves and warmer colors arrive. Instead, the balance shifts slowly, minute by minute, as the sun's angle lowers and the atmospheric path lengthens. The blues thin, the yellows soften, and warmer tones begin to dominate simply because they are the wavelengths most capable of surviving the longer journey intact. The sky responds to this change with calm precision. Near the horizon, where the path through air is longest, blue light is scattered most efficiently, allowing oranges and reds to emerge more clearly. Higher above, where the light still travels a shorter route, cooler tones may remain visible, creating smooth gradients rather than sharp boundaries. The sky becomes a quiet record of distance and direction. There is nothing for the sky to decide and nothing for light to adjust. Each wavelength follows the same physical rules it always has. Blue light scatters, longer wavelengths persist, and the atmosphere patiently reshapes what we see. These changes do not hurry, and they do not announce themselves. They simply unfold, preparing the stage for the deeper colors that will soon settle along the edge of day. As cooler tones are gradually scattered away from the direct path of sunlight, the colors that remain begin to reveal something quietly important about the nature of light itself. Red and orange hues belong to the longer wavelengths within the visible spectrum, and these wavelengths interact with the atmosphere in a different, calmer way. They are not immune to scattering, but they are far less easily redirected, allowing them to persist even as the sun's light travels through increasingly thick layers of air. Longer wavelengths carry less energy per oscillation than shorter ones, and this makes them less sensitive to the tiny gas molecules that fill the atmosphere. When red and orange light encounters nitrogen and oxygen, it is more likely to continue forward rather than being sent off in another direction. Over long distances, this difference becomes noticeable. While blues are gently pulled away from the direct beam, reds remain, quietly enduring the extended journey toward the horizon. This persistence is why sunsets feel warm in color rather than cool. As sunlight passes through more atmosphere, the balance of wavelengths shifts toward those that scatter least. What reaches the ground is not newly created color, but a filtered remainder, shaped by distance and interaction. The atmosphere acts like a soft sieve, allowing certain wavelengths to pass through more easily, while others are spread thin across the sky. The effect becomes strongest near the horizon, where sunlight travels through the greatest thickness of air. Here, red and orange wavelengths dominate the remaining light, producing the glowing bands that often define sunset scenes. The sun itself appears deeper in color for the same reason, not because its surface has changed, but because much of its shorter wavelength light has been scattered away long before it reaches the eye. This behavior remains consistent regardless of location or season, whether viewed from a coastline, a city street, or an open field. The same physical rules apply. Variations in color intensity come from differences in atmospheric conditions, not from changes in how light behaves. Longer wavelengths always retain their ability to travel farther through air, carrying warmth and depth into the final moments of daylight. Even when the sky takes on dramatic shades, the process behind them remains gentle and steady. No force pushes red light forward, and no barrier blocks the blues. Each wavelength simply responds to its environment, interacting according to size, energy, and distance. Over time, the accumulation of these quiet interactions becomes visible as color. You don't need to imagine these wavelengths moving or competing with one another. They travel together, separating only through circumstance rather than intention. As evening continues, the light that remains grows warmer, not because something new is arriving, but because what travels farthest is what stays behind. The reds linger calmly, carrying the last visible warmth of the day toward the edge of night. As the balance of light continues to shift, the sun itself begins to appear different, even though nothing about it has changed. Its surface remains just as bright and active as it was at midday, releasing the same steady flow of energy into space. The transformation we notice is not occurring at the sun, but along the long, angled path its light must now travel before reaching the ground. When much of the shorter wavelength light has been scattered away, the remaining light that reaches the eye carries a warmer tone. Yellows deepen into orange, and orange gradually gives way to red. This change happens slowly, almost imperceptibly, as the sun lowers further, allowing the filtering effects of the atmosphere to become more pronounced. The color shift is a quiet indicator of distance rather than intensity. The sun can appear softer and less glaring at this time, because a significant portion of its light has been redirected elsewhere. Scattered light fills the sky instead of arriving directly, reducing contrast and brightness. What remains feels gentler to look at, even though the total amount of light being produced by the sun has not diminished. The atmosphere simply redistributes it more widely. This warm appearance is influenced by perception as well as physics. Against a darker horizon and a sky already losing its brightness, the remaining light feels richer and more saturated. The human mind interprets color in context, comparing what it sees to the surrounding environment. As the sky darkens, warm tones stand out more clearly, giving the sun a deeper, heavier presence near the horizon. Atmospheric conditions can subtly shape this effect. Clear air often produces cleaner, more defined color changes, while haze or fine particles can deepen reds and soften edges. These variations are not dramatic shifts in process, but small adjustments in how much light is scattered and where it goes. The rules remain the same, but their expression changes slightly from one evening to the next. Even when the sun appears vividly red, its light is still traveling in straight lines, responding only to interaction and distance. There is no bending of intention, no transformation at the source. What we see is a filtered view, shaped by the accumulated effect of countless tiny encounters between light and air. You don't need to watch the sun closely to notice this change. It happens whether attention is present or not, guided by geometry and motion rather than observation. As the sun continues to lower, its color deepens naturally, marking the slow passage of time with warmth rather than urgency, and offering a final softened glow before daylight gently recedes. All of the color changes that unfold near evening depend on the quiet presence of the atmosphere itself. Earth's air may feel empty or invisible, but it is filled with countless molecules, mostly nitrogen and oxygen, drifting constantly without pattern or pause. These molecules are far too small to be seen, yet they play a central role in shaping how light behaves as it moves through the sky. Each air molecule acts as a tiny point of interaction for passing light. When sunlight encounters these molecules, the light's electric field causes the molecules to momentarily vibrate, re-emitting the light in new directions. This process happens instantly and without energy loss, and it occurs trillions of times across the atmosphere at any given moment. The molecules do not store light or alter it intentionally. They simply respond according to basic physical laws. Because nitrogen and oxygen molecules are much smaller than the wavelengths of visible light, they scatter shorter wavelengths more efficiently than longer ones. This size relationship is what makes Rayleigh scattering possible and consistent. The molecules themselves never change size or behavior from day to day, which is why the overall pattern of sky color remains reliable even as individual sunsets vary. Clear air often produces the most balanced and delicate sunset colors. When the atmosphere contains mostly gas molecules and very few larger particles, scattering happens in a predictable, orderly way. Blues are redirected across the sky, and warmer wavelengths remain in the direct path, creating smooth gradients rather than sharp contrasts. The result is often a clean transition from warm horizons to cooler tones above. Even in the calmest conditions, air is never perfectly uniform. Temperature differences, pressure changes, and gentle currents create subtle variations in molecular density. These small fluctuations slightly alter how light is scattered from one moment to the next, adding softness and complexity to the sky without disrupting the underlying process. The atmosphere behaves like a living filter, steady but never rigid. Nothing about this interaction requires force or effort. Light moves forward, molecules respond, and the result emerges naturally. There is no accumulation of tension, no build-up toward a dramatic outcome. The colors we see are simply the visible trace of countless tiny exchanges happening quietly overhead. You don't need to imagine the molecules or follow their motion. They drift freely, responding only when light passes through them. Together, they sculpt the sky gently and continuously, shaping each sunset not with intention, but with patience, allowing color to emerge as a calm consequence of presence and distance. Beyond the ever-present molecules of air, the atmosphere also carries a shifting collection of much larger particles, so small they often go unnoticed, yet large enough to influence the colors of sunset in subtle ways. These particles include dust lifted from dry ground, salt carried inland from oceans, smoke from distant fires, and tiny droplets formed through natural chemical processes. Together, they form a thin veil that light must also pass through as evening approaches. Unlike individual gas molecules, these particles are closer in size to the wavelengths of visible light. Because of this, they scatter light differently, favoring longer wavelengths more than shorter ones. When sunlight encounters fine particles, reds and oranges are scattered more efficiently, while blues continue to disperse across the sky. This type of scattering can deepen warm colors near the horizon, sometimes producing vivid reds, pinks, or purples that feel richer than those seen on clearer days. This effect becomes especially noticeable after large volcanic eruptions or during periods of widespread smoke. In such cases, fine particles can remain suspended in the atmosphere for weeks or even months, subtly altering sunsets across wide regions of the planet. Historical records and paintings often reflect these periods, showing unusually intense sunset colors that later match known atmospheric events. The science behind these changes was only understood much later, but the visual record remained quietly accurate. Even on ordinary evenings, small variations in particle concentration can influence how colors appear. A slightly dustier sky may soften transitions between hues, while a cleaner atmosphere produces sharper gradients. These differences do not override the basic rules of light scattering, but they add texture and variety, ensuring that no two sunsets feel exactly alike. Particles do not create new colors, and they do not replace the role of air molecules. Instead, they layer their influence gently on top of existing processes, nudging light in ways that favor warmth and depth. Their presence acts like an additional filter, subtle and temporary, reshaping the final balance of color that reaches the eye. There is nothing deliberate in this interaction. Particles drift where air currents carry them, and light responds as it always does, changing direction when conditions allow. Together, they add complexity without disruption, enriching the sky without altering its rhythm. You don't need to identify the particles or trace their origin. They come and go naturally, leaving quiet signatures in the evening light. As the sun continues to lower, these fine companions in the air help guide warmth toward the horizon, allowing sunsets to deepen gently, one softened shade at a time. Along with air molecules and fine particles, the atmosphere also carries water in many quiet forms. Some of it exists as invisible vapor, while some gathers into tiny droplets too small to fall as rain. Even when the sky appears clear, moisture is almost always present, moving slowly with air currents and subtly influencing how light spreads as the day comes to an end. Water droplets interact with light differently than gas molecules do. Because they are larger in size, they tend to scatter light more broadly, diffusing it rather than redirecting it sharply. This diffusion softens edges and blends colors together, often giving humid sunsets a smoother, more pastel quality. Instead of crisp boundaries between hues, the sky may appear gently brushed, with colors flowing into one another without clear lines. On evenings with higher humidity, light can spread farther across the sky, lingering longer after the sun has dipped below the horizon. Moisture helps carry scattered light sideways and upward, extending the glow of sunset into the early moments of twilight. This is why humid air can make sunsets feel slower, as though the light is reluctant to leave, even though the same physical processes are still at work. Haze often accompanies humidity, especially near the surface where air is cooler and denser. This haze is made up of microscopic water droplets suspended in the air, each acting as a tiny diffuser. Together, they scatter warm light outward, enhancing oranges and pinks while softening contrast. The result is not brighter light, but more evenly distributed light, spread gently across a wider portion of the sky. In drier air, these effects are reduced. Light travels with less diffusion, producing sharper transitions and clearer gradients. Neither condition is more correct or more natural than the other. They are simply different expressions of the same interaction between light and atmosphere, shaped by how much moisture the air happens to hold at that moment. Water vapor itself is constantly changing, rising and falling with temperature and pressure. It gathers quietly in low areas during the evening, especially as the ground cools. These slow shifts can subtly alter how light behaves minute by minute, adding depth and softness without changing the overall pattern of sunset. You don't need to sense the moisture or measure it to feel its influence. It works silently, spreading light with patience and ease. As evening continues, water vapor helps guide the last warmth of the day outward and upward, smoothing the sky's colors into a calm, lingering glow that fades without hurry. As daylight thins and the sun lowers, clouds begin to play a more visible role in shaping the evening sky. Though they often seem like passive features drifting overhead, clouds act as broad, floating surfaces that reflect, scatter, and redirect light in gentle ways. Their influence becomes most noticeable near sunset, when the angle of sunlight allows clouds to catch and hold color that would otherwise pass by unnoticed. Clouds form at different heights within the atmosphere, and their altitude matters. High clouds, made mostly of ice crystals, sit well above much of the denser air below. When low-angle sunlight reaches them, it has already been filtered by a long atmospheric path, rich in warmer wavelengths. These clouds reflect that filtered light back toward the ground, often glowing with soft pinks, golds, and pale reds. Because they are high and thin, their colors can appear delicate and expansive, spreading warmth across large portions of the sky. Lower clouds, composed mainly of water droplets, interact with light more diffusely. They scatter light in many directions, softening its intensity and blending colors together. When these clouds sit near the horizon at sunset, they can catch the deepest reds and oranges, appearing briefly illuminated before fading into shadow. Their edges may glow while their centers darken, revealing depth through contrast rather than brightness. The shape and texture of clouds also matter. Thin, wispy clouds allow light to pass through while scattering it gently, creating layered color effects. Thicker clouds block direct light more strongly, casting broad shadows while reflecting warm tones along their edges. This interplay between light and form adds variation to the sky without altering the underlying physics guiding it. Clouds do not generate color on their own. They simply reveal what is already present in the light that reaches them. As sunlight becomes warmer and more directional near sunset, clouds act like temporary canvases, displaying that warmth briefly before it fades. Their movement, driven by slow air currents, means that these displays are always changing, never fixed in place. Even a mostly clear sky can contain thin cloud layers that subtly influence sunset colors. These layers may not be obvious at first glance, yet they contribute to the overall softness and spread of light. Their presence helps explain why some sunsets feel more textured or dynamic than others, even under similar conditions. You don't need to follow the clouds or name their forms. They drift naturally, responding to forces far removed from the quiet light they reflect. As the sun continues its descent, clouds catch the last filtered rays of day and return them gently to the sky, holding color just a little longer before letting it go. After the sun slips below the horizon, daylight does not end all at once. Instead, it lingers, unfolding through a series of gradual stages known collectively as twilight. This lingering light exists because sunlight continues to scatter through the atmosphere, even when the sun itself is no longer directly visible. The sky remains softly illuminated, guided by geometry rather than presence. Twilight is often described in layers, each defined by how far below the horizon the sun has moved. In the earliest stage, known as civil twilight, the sun sits just below the edge of the earth, and scattered light is still strong enough to illuminate much of the sky. During this time, warmer tones may fade, but the landscape remains visible, and the sky often holds pale blues mixed with lingering gold near the horizon. As Earth continues to turn, the sun sinks farther below the horizon, and nautical twilight begins. The path sunlight must travel now stretches even longer through the atmosphere, thinning further as it goes. Scattered light becomes dimmer and cooler in tone, and the sky shifts toward deeper blues. The contrast between horizon and overhead sky softens, and the remaining light feels more diffuse, spread gently rather than directed. Astronomical twilight follows, marking the final stage before full night. At this point, the sun is far enough below the horizon that only the faintest scattered light remains. The atmosphere still redirects a small amount of sunlight, but it is no longer strong enough to brighten the sky noticeably. Stars begin to appear more clearly, and the sky transitions toward darkness through subtle gradients rather than abrupt change. These stages are not boundaries, and they are not always easy to distinguish by sight alone. They exist as convenient ways to describe how sunlight interacts with the atmosphere at increasing distances below the horizon. The physical process remains the same throughout. Light continues to scatter, gradually diminishing as its path length grows and its intensity thins. The duration of twilight depends on location and season. Near the equator, twilight passes relatively quickly, while at higher latitudes it can stretch on, sometimes lasting for hours during certain times of year. This difference arises from the angle at which the sun moves relative to the horizon, not from changes in atmospheric behavior. You don't need to track these stages or notice when one ends and another begins. Twilight flows naturally, guided by Earth's rotation and the steady scattering of light. Even after the sun has disappeared, its presence lingers quietly in the sky, fading layer by layer until the last traces of day dissolve gently into night. The way a sunset unfolds is shaped not only by the atmosphere, but also by where you are standing on the planet. Earth's curved surface and tilted axis mean that the sun does not follow the same path across the sky everywhere. Instead, its angle of descent changes with latitude, quietly influencing how long sunsets last and how their colors spread across the horizon. Near the equator, the sun rises and sets along a relatively steep path. It moves downward toward the horizon at a sharper angle, crossing it more directly. Because of this, the transition from daylight to night happens more quickly. Sunsets in these regions often feel brief, with colors appearing and fading in a shorter window of time, even though the same scattering processes are taking place. At higher latitudes, the sun's path is much shallower. Rather than dropping straight down, it slides along the horizon at an angle, lingering near the edge of the sky. This shallow geometry stretches the length of sunset, giving light more time to travel through the thickest layers of the atmosphere. As a result, color changes unfold slowly, and twilight can last significantly longer. This extended path also affects how light is filtered. When the sun remains low for longer periods, its light consistently travels through dense atmospheric layers, allowing scattering to act continuously rather than briefly. Warm tones may persist, deepen, and spread wider across the sky, creating long, gradual gradients that shift almost imperceptibly over time. Seasonal changes amplify these effects. As Earth orbits the sun, the tilt of its axis alters the apparent path the sun takes across the sky. In summer, at high latitudes, the sun may barely dip below the horizon, producing extended twilight and prolonged sunset colors. In winter, the same locations experience faster descents and shorter transitions, even though the atmosphere itself behaves the same way. These differences are geometric rather than chemical or energetic. The sun does not change its brightness based on latitude, and the atmosphere does not rearrange itself. Only the angle of observation shifts, stretching or compressing the timeline over which familiar processes unfold. You don't need to know your latitude or picture the Earth turning beneath you. Wherever you are, the sun follows a path determined by the planet's shape and tilt, carrying light along routes that shape the evening quietly and consistently. As the horizon receives the sun at different angles around the world, sunsets adapt gently, revealing how geometry alone can influence the pace of fading light. As the year moves forward, sunsets shift not only in timing, but in position and character as well. This seasonal change is guided by Earth's axial tilt, a steady lean of about 23.5 degrees that remains constant as the planet orbits the sun. While the tilt itself never changes, its orientation relative to the sun does, quietly reshaping how sunlight reaches the atmosphere over the course of the year. During different seasons, the sun's apparent path across the sky rises higher or lower at midday and approaches the horizon at varying angles in the evening. In summer, the sun tends to follow a longer, higher arc, often descending more slowly near sunset, especially at mid to high latitudes. This extended path allows sunlight to linger at low angles, increasing the time it spends traveling through dense layers of air and gently enhancing the depth of evening colors. In winter, the sun's path is lower and more compressed. It approaches the horizon at a steeper angle, shortening the transition between day and night. With less time spent skimming the atmosphere, sunsets may appear briefer, sometimes sharper in contrast, even though the same scattering processes remain at work. The difference lies in duration rather than mechanism. Seasonal shifts also influence atmospheric conditions themselves. Cooler months often bring clearer air in many regions, with fewer airborne particles and lower humidity. These conditions can produce cleaner, more defined gradients between colors, while warmer seasons may introduce more moisture and fine particles, softening transitions and spreading warm tones more widely across the sky. The position of sunset along the horizon changes throughout the year as well. The sun does not set in the same place each evening, but gradually moves north or south along the horizon depending on the season. This slow migration alters the way light interacts with local landscapes and cloud patterns, subtly changing how color appears from one time of year to the next. None of these changes require dramatic forces or sudden shifts. They arise from steady motion, repeated over long cycles, guided by Earth's orientation in space. The tilt that gives rise to seasons also shapes the rhythm of sunsets, stretching or compressing the evening without altering its underlying calm. You don't need to track the calendar or notice the sun's shifting position to feel these changes. They happen quietly, layered into the passing of weeks and months. As the planet continues its gentle orbit, sunsets adapt in pace and tone, reflecting the slow geometry of Earth's tilt through soft variations of light and color. As the sun approaches the horizon, it often appears larger than it did earlier in the day, resting heavily against the edge of the sky. This impression can feel striking, as though the sun has expanded or drawn closer to Earth. In reality, its physical size and distance remain unchanged. What shifts is perception, shaped quietly by context and comparison rather than by light itself. One of the primary reasons for this effect is an optical illusion created by the human mind. When the sun is high in the sky, it appears isolated, surrounded by vast open space with little nearby reference. Near the horizon, however, it is seen alongside distant objects such as trees, buildings, mountains, or clouds. The mind compares the sun to these familiar elements and interprets it as larger, even though its angular size on the retina remains nearly constant. Atmospheric effects add a subtle layer to this illusion. As sunlight travels through denser air near the horizon, it can be slightly refracted, bending very gently as it passes through layers of differing temperature and density. This refraction can flatten the lower edge of the sun, giving it a wider, heavier appearance. The effect is small, but it contributes to the overall impression of size and presence. The sun's warmer color at sunset also plays a role. Reds and oranges tend to feel heavier and more substantial than cooler tones, a psychological association rooted in human perception rather than physics. Against a darkening sky, these warm hues stand out more strongly, drawing attention and reinforcing the sense that the sun occupies more space than it did earlier. Photography confirms this illusion. Images taken with the same lens throughout the day show that the sun's size remains essentially the same from noon to sunset. What changes is not the object, but the frame of reference surrounding it. The mind fills in meaning based on contrast, proximity, and expectation, creating an experience that feels vivid even when the measurements remain steady. This illusion is not a flaw in perception, but a natural feature of how the mind interprets the world. It allows us to understand scale and distance quickly, even when precise measurement is not possible. At sunset, this ability simply reveals itself more clearly, transforming a familiar object into something that feels momentarily larger and closer. You don't need to question what you see or correct the impression. The sun remains exactly where it has always been, while perception gently reshapes the experience. As it rests along the horizon, appearing fuller and slower, the illusion settles naturally, offering a final sense of weight and presence before the light continues its quiet descent. The colors of sunset do not exist only in the sky. They are completed within the human mind, where light becomes experienced through interpretation rather than measurement. While physics determines which wavelengths reach the eye, perception decides how those wavelengths are understood, compared, and remembered. This quiet partnership between light and the mind plays a subtle role in why sunsets feel so rich and emotionally resonant. Human vision does not respond to color in isolation. Instead, it constantly compares what it sees to surrounding tones and levels of brightness. As daylight fades, overall light levels drop, and the mind adjusts its sensitivity in response. Cooler tones diminish more quickly, while warmer colors remain more noticeable, standing out against the darkening sky. This shift is not a change in the light itself, but in how strongly different colors register within perception. Contrast also becomes more pronounced in low light. Warm hues near the horizon appear deeper when set against cooler blues above or the growing darkness below. The mind amplifies these differences, enhancing separation between colors even when their physical intensity is modest. This is why sunsets often feel more vivid than photographs can capture. A camera records wavelengths faithfully, but it does not interpret context in the same way a human does. As light grows softer, the visual system transitions gradually from color-dominant vision toward greater reliance on brightness and contrast. During this transition, colors that remain visible take on greater significance. Reds and oranges linger longer within perception, not only because they survive atmospheric filtering, but because the visual system continues to register them more clearly under dim conditions. Memory and expectation also shape how sunset colors are experienced. The mind carries associations built from past observations, linking certain hues with calm, warmth, or closure. When these colors appear again, they are recognized quickly and felt more strongly, even if their physical properties are unchanged. Perception layers meaning gently on top of sensation, without effort or awareness. None of this requires conscious thought. The visual system adjusts automatically, balancing sensitivity and contrast as conditions change. The result is a smooth, continuous experience, rather than a sequence of technical adjustments. The sky's colors seem to deepen naturally, guided by perception, just as much as by scattering and distance. You don't need to analyze the colors or name them as they fade. The mind responds quietly, shaping what is seen into something cohesive and complete. As evening settles in, perception softens alongside the light, allowing color to become feeling, and feeling to drift calmly toward rest. As daylight gradually gives way to evening, the changing quality of light does more than alter the colors of the sky. It also provides gentle signals to the body, quietly aligning internal rhythms with the time of day. These signals are not commands or instructions, but subtle cues that have accompanied life on Earth for millions of years, repeating with calm regularity. Throughout the day, bright, blue-rich light supports alertness by interacting with specialized cells in the eyes that respond to overall light levels rather than detailed images. As the sun lowers and shorter wavelengths are scattered away, the remaining light becomes warmer and less intense. This shift reduces stimulation to those light-sensitive pathways, allowing the body to begin easing away from the heightened alertness of daytime. The gradual nature of sunset is important. Because the change in light is slow and predictable, the transition it supports is also unhurried. There is no sudden drop in illumination outdoors, only a steady softening that unfolds over time. This allows biological systems to adjust smoothly, responding to changing conditions without disruption or urgency. Warm-toned evening light contains fewer short wavelengths, which are more effective at signaling daytime conditions. As those wavelengths fade, the balance of sensory input shifts naturally. This change is observed across many species, not just humans, reflecting a shared response to the predictable rhythm of light and dark created by Earth's rotation. The atmosphere plays a key role in shaping this experience. By filtering and redistributing light at sunset, it ensures that evening does not arrive abruptly. Scattered light continues to glow long after the sun itself has disappeared, stretching the transition and allowing internal rhythms to settle gradually rather than suddenly. None of this requires awareness or effort. The body responds automatically to the changing environment, guided by patterns that repeat daily. The sky's colors, the softening light, and the lengthening shadows all work together as quiet signals, reinforcing the sense that the day is drawing to a close. You don't need to think about these rhythms or track their timing. They unfold naturally, carried by light and motion rather than intention. As the evening deepens, the sky and the body respond in parallel, both easing gently into a slower state, guided by the same steady, fading light that has always marked the end of day. As evening deepens, the fading of light is often accompanied by a quieter shift in how the world is perceived as a whole. While sunsets are most visible through changing colors in the sky, they also mark a gradual easing of sensory intensity across the environment. This change does not arrive as silence or stillness all at once. Instead, it unfolds slowly, guided by the same steady processes that soften the light itself. During daylight hours, strong sunlight creates sharp visual contrast. Surfaces reflect brightly, edges are clearly defined, and shadows fall with crisp boundaries. This clarity demands attention. The visual system works continuously to separate objects from their surroundings, tracking movement and detail with precision. As the sun lowers, this visual sharpness begins to dissolve. Light spreads more evenly through the atmosphere, glare diminishes, and contrasts soften. Objects appear less segmented from their background, and the visual field becomes smoother and less demanding. This softening of vision influences how other senses are experienced. When visual input becomes less intense, the mind naturally redistributes attention. Sounds that once stood out sharply may begin to blend together, losing their urgency. The environment does not grow silent, but auditory details feel less intrusive, more evenly layered. Distant sounds may become more noticeable for a moment, then gently recede as perception relaxes. Atmospheric changes near sunset support this shift. As the ground cools, air near the surface becomes more stable, reducing turbulent motion. Wind often slows or changes character, decreasing the constant background noise produced by moving air during the day. Under these calmer conditions, sound can travel farther, but it often arrives softened rather than sharp, spreading gently instead of cutting through space. Movement is also perceived differently as light fades. reduced contrast and softer illumination make motion appear smoother and less abrupt. Changes in position are still present, but they register with less intensity. The world may seem to slow down, even though its pace remains unchanged. This impression is created not by mechanics, but by perception, shaped by the way fading light reduces the need for constant sensory updating. The human mind continuously filters sensory information, determining what requires focus and what can fade into the background. As evening progresses and stimulation decreases across multiple senses at once, this filtering becomes easier. Fewer signals compete for attention, allowing awareness to widen rather than fixate. Attention loosens naturally without instruction or effort. Even the absence of strong visual cues contributes to this quieting. As details become less distinct, the environment feels less demanding. There is less to track, less to interpret, and less to respond to. This does not remove information from the world, but it changes how urgently that information is presented to the senses. None of this depends on conscious intention. The evening does not request calm, and it does not remove activity from the world. Instead, it reshapes conditions gently. Light dims, contrast softens, air steadies, sound disperses, and motion feels less sharp. These changes mirror the same gradual rhythm seen in the sky, where color fades not abruptly, but through patient transition. You don't need to seek quiet or create stillness. The environment offers it naturally as daylight recedes. As the sky continues to darken and scattered light thins further, sensory experience settles into a quieter balance, where stillness feels less like an absence and more like a gentle continuation of the day's slow, unhurried close. While sunsets on Earth feel familiar, shaped by air, moisture, and motion we experience every day, the same fundamental physics plays out across the solar system in strikingly different ways. Wherever light passes through an atmosphere, it interacts with particles and gases, scattering and filtering according to their size, composition, and density. By studying sunsets on other worlds, scientists gain insight into how atmospheres behave and how unique Earth's balance truly is. On Mars, sunsets look noticeably different from those on Earth. Instead of glowing red near the horizon, Martian sunsets often appear bluish around the sun, with warmer tones spread farther across the sky. This reversal happens because Mars's atmosphere is thin and filled with extremely fine dust particles. These particles scatter longer wavelengths more efficiently than shorter ones, allowing blue light to remain concentrated near the sun, while reds disperse outward. The same rules of scattering apply, but the scale and particle size shift the outcome. Venus presents another contrast. Its atmosphere is thick, dense, and filled with clouds of sulfuric acid droplets. Sunlight traveling through this heavy atmosphere is scattered repeatedly, diffused in many directions before ever reaching the surface. As a result, direct sunlight is muted, and sunsets are less about sharp color changes and more about gradual dimming. The sky takes on a uniform, hazy glow, where light fades slowly, rather than transitioning through vivid bands of color. Titan, Saturn's largest moon, offers yet another variation. Its atmosphere is dense and rich in complex organic molecules, creating an orange-brown haze that filters sunlight strongly. Sunsets on Titan are subdued and dim, with much of the visible spectrum absorbed or scattered long before it reaches the surface. What remains is a soft amber twilight, shaped by chemistry very different from Earth's, yet governed by the same physical principles. Even planets without substantial atmospheres reveal something through the absence of sunsets. On the Moon, for example, the sun sets abruptly. Without air to scatter light, there is no lingering twilight, no gradual fading of color. Day shifts to night sharply, emphasizing how much of Earth's sunset experience depends on the presence of an atmosphere rather than the sun itself. By comparing these worlds, scientists learn how particle size, atmospheric thickness, and composition influence light. Instruments on board spacecraft analyze the color and intensity of light near planetary horizons, allowing researchers to infer what an atmosphere is made of and how it behaves. In this way, sunsets become tools for discovery, revealing invisible properties through visible change. Earth's sunsets sit in a delicate balance. The atmosphere is thick enough to scatter light richly, yet clear enough to allow color to remain vivid. Water vapor, dust, and clouds add variation without overwhelming the scene. This balance is not guaranteed elsewhere, and it is what gives Earth's sunsets their distinctive warmth and depth. You don't need to imagine standing on these distant worlds to appreciate the comparison. Knowing that the same sunlight behaves differently across the solar system highlights how much of what we see at sunset is shaped locally by the air surrounding us. As evening light fades on Earth, it carries with it the quiet signature of a planet uniquely suited to turn simple physics into lingering color and calm. In the modern world, sunsets are shaped not only by natural processes, but also by subtle changes in the composition of the air itself. As human activity introduces additional particles and gases into the atmosphere, the way light scatters near the horizon can shift in quiet but noticeable ways. These changes do not alter the fundamental physics of sunset, but they can influence how strongly certain colors appear and how evenly light is distributed across the sky. In urban and industrial regions, the atmosphere often contains higher concentrations of fine particles produced by vehicles, manufacturing, and energy generation. These particles are typically small enough to remain suspended for long periods, drifting slowly with air currents. When sunlight passes through air rich in these particles, longer wavelengths such as red and orange are scattered more efficiently, often intensifying warm hues near the horizon while muting cooler tones above. This is why sunsets near large cities can sometimes appear unusually vivid, glowing with deep reds or purples, even on otherwise clear evenings. The added particles act as an additional scattering layer, enhancing certain colors through diffusion rather than clarity. While these sunsets can look dramatic, the effect comes from the same scattering mechanisms seen with dust or smoke, only applied more persistently due to long-term atmospheric conditions. Rural and remote areas often display a different character. With fewer airborne particles, the atmosphere behaves more like a clean scattering medium dominated by gas molecules. Sunsets in these regions tend to show smoother gradients and clearer transitions between colors, with less diffusion and more separation between warm and cool tones. Neither experience is more correct than the other. They are simply different expressions of how light responds to its environment. Over longer timescales, gradual changes in atmospheric composition can subtly alter how sunsets look from decade to decade, Increased concentrations of aerosols can shift average color balance, while efforts to reduce air pollution may slowly return skies to earlier conditions. These changes are often too slow to notice day by day, but they leave faint signatures when viewed across years or generations. Scientists study these effects carefully, using long-term observations of sky color, satellite measurements, and ground-based sensors. By tracking how light scattering changes over time, researchers can infer shifts in atmospheric clarity and particle concentration. In this way, sunsets become quiet indicators of broader environmental patterns, reflecting invisible changes through visible color. Despite these influences, the essential rhythm of sunset remains unchanged. Earth still turns, the sun still lowers, and light still travels through air according to the same physical rules. Added particles may adjust the balance, but they do not interrupt the process. The sky continues to respond patiently, reshaping light moment by moment as evening approaches. You don't need to judge or analyze what you see when the sky glows at dusk. Each sunset reflects the conditions of its moment, shaped by air, light, and distance. As modern skies continue to evolve, sunsets adapt quietly, carrying forward the same gentle physics while revealing, in color and tone, the subtle story of the air we live within. While sunsets are often experienced as moments of quiet beauty, they are also valuable scientific events that unfold with reliable precision. To scientists, the slow change of color near the horizon provides a natural experiment, repeated daily, revealing how light behaves as it passes through Earth's atmosphere. By observing these transitions carefully, researchers can learn about air composition, particle size, and even large-scale environmental changes, all through the gentle fading of daylight. One of the most important tools used to study sunsets is spectroscopy. Spectrometers measure light by separating it into its component wavelengths, allowing scientists to track how different colors weaken or persist as the sun lowers. As sunlight travels through a longer atmospheric path near the horizon, specific wavelengths are scattered or absorbed at predictable rates. By recording these changes, scientists can identify which gases and particles are present in the air and how strongly they influence the light passing through. Ground-based observatories often play a key role in this work. Instruments positioned with a clear view of the horizon monitor by sunset light, minute by minute, capturing gradual shifts that are too subtle for the human eye to quantify accurately. These measurements reveal how scattering increases as the sun approaches the horizon, and how the balance between direct and scattered light changes over time. The slow pace of sunset makes it especially useful for this type of observation, as it allows data to be collected continuously without abrupt transitions. Satellites provide a broader perspective. From orbit, instruments can observe sunsets occurring across vast regions of the planet at once. By measuring how light reflects and scatters along the edge of Earth's atmosphere, satellites offer insight into global atmospheric conditions. They can compare sunsets over oceans, forests, deserts, and cities, identifying patterns linked to humidity, pollution, and seasonal variation. This global view helps scientists understand how local conditions fit into larger atmospheric systems. Laser-based techniques are sometimes used alongside these observations. By sending controlled pulses of light upward and measuring how that light scatters back toward the surface, researchers can estimate the concentration and altitude of particles in the atmosphere. This information helps explain why sunsets appear especially vivid on some evenings and more muted on others, even when weather conditions seem similar. These measurements provide a vertical profile of the atmosphere, revealing layers that are otherwise invisible. Long-term data collection is especially important in sunset research. Scientists often compare records gathered over years or decades to identify slow trends in atmospheric clarity and composition. Subtle shifts in average sunset color or brightness can indicate changes in aerosol concentration, air quality, or large-scale circulation patterns. Because sunsets occur daily and follow predictable geometry, they serve as consistent reference points for tracking gradual environmental change. Historical records also play a role. Written descriptions, early photographs, and paintings sometimes preserve evidence of unusual atmospheric conditions, such as periods following major volcanic eruptions. Scientists have used these records to confirm past events, linking vivid historical sunsets to known increases in airborne particles. In this way, observations made long before modern instruments existed still contribute to present-day understanding. Despite the precision involved in studying sunsets, the process remains non-invasive. Scientists do not need to alter the environment or interfere with natural systems. They simply observe, measure, and interpret what the sky already offers. Sunset provides a built-in experiment, repeating itself every evening with slight variations, allowing careful study without disruption. None of this scientific attention diminishes the experience of watching a sunset. Knowing that instruments elsewhere are measuring the same fading light does not change how it feels in the moment. The sky continues its slow transition regardless of observation, responding only to distance, air, and motion. You don't need to think about data or instruments as evening arrives. The science unfolds quietly in the background, while the visible changes remain gentle and familiar. As the sun continues to lower and the sky responds with softened color and thinning light, the same calm sequence plays out, offering both understanding and stillness, without asking for attention from either one. Long before the science of light and atmosphere was understood, sunsets were already being carefully observed. Across cultures and centuries, people watched the sky change at the end of the day and sensed that something meaningful was taking place, even if the reasons were not yet clear. The slow fading of daylight became a shared experience, repeated endlessly, shaping stories, symbols, and quiet rituals tied to the close of each day. In early societies, sunsets often marked boundaries. They signaled the end of work, the return home, and the shift from activity to rest. Without artificial lighting, the disappearance of the sun carried practical importance. Night brought limited visibility and heightened uncertainty, so the gradual dimming of the sky served as a natural warning, allowing time to prepare. This predictable rhythm helped structure daily life long before clocks existed. Many ancient cultures interpreted sunset colors as messages or signs. Deep reds and purples were sometimes associated with fire, blood, or transformation, while softer golds and pinks were seen as symbols of peace or completion. These interpretations were shaped by observation rather than measurement, rooted in how the colors felt rather than what caused them. Even without scientific language, people recognized that sunsets followed patterns appearing differently across seasons and locations. Artists, long before scientists, became some of the most attentive observers of sunset light. Painters noticed how colors softened as the sun lowered, how shadows lengthened, and how the sky shifted from blue to warm tones and then to deep twilight. These visual records captured atmospheric behavior with surprising accuracy, even when the mechanisms behind it remained unknown. In some cases, historical paintings have later helped scientists identify periods of increased volcanic activity or atmospheric haze based on unusually vivid sunset colors. Written accounts from travelers and explorers often describe sunsets as markers of unfamiliar environments. Deserts, oceans, mountains, and polar regions each produce distinctive evening skies, shaped by local air conditions and geography. These descriptions reveal an intuitive understanding that the sky responded to place, even if the physics behind that response had not yet been discovered. The sky became a quiet map, reflecting unseen properties of the air and land below. As scientific thinking developed, sunsets slowly transitioned from symbols to subjects of study. Early astronomers and natural philosophers began to question why the sky changed color, why light lingered after the sun had set, and why evening hues differed from those seen at dawn. These questions laid the groundwork for later discoveries about scattering, wavelength, and atmospheric composition. The beauty of sunset did not disappear under analysis. Instead, it became more deeply understood. Despite advances in explanation, the emotional weight of sunsets remained. Even with knowledge of physics, people continued to pause and watch the sky at the end of the day. The predictability of sunset offered comfort, while its variations prevented it from becoming dull. Each evening repeated the same basic process, yet never looked exactly the same, balancing reliability with subtle novelty. In modern times, sunsets still hold cultural significance. They appear in photography, film, literature, and shared moments, often symbolizing closure, reflection, or transition. Social habits may change, and technology may reshape daily routines, but the visual language of sunset remains widely understood. The sky continues to provide a shared reference point, one that requires no explanation to feel meaningful. What makes this enduring connection possible is the slow pace of sunset itself. Unlike sudden events, sunsets unfold gradually, allowing time for attention to settle. The sky does not rush its transformation. It offers color, then fades it, guiding awareness gently from brightness to dimness. This rhythm has remained unchanged across generations, even as interpretations have evolved. You don't need to carry the stories or symbols of the past to experience this moment. The same sky that once inspired myths and paintings continues to respond to light and air in the same patient way. As evening deepens and colors recede, sunset remains what it has always been, a quiet meeting point between observation and reflection, where history, perception, and physics overlap without effort, easing the day gently toward its end. Every sunset is the visible result of motion, though that motion is easy to forget while watching the sky change. The sun does not move closer to the horizon on its own, and the atmosphere does not shift into evening deliberately. Instead, sunset happens because Earth is turning steadily and continuously, carrying each location on its surface away from direct sunlight. What appears as fading light is, in reality, the quiet consequence of planetary rotation, made visible through color and shadow. Earth completes one full rotation, approximately every 24 hours. This rotation is smooth and unbroken, with no pauses or accelerations at sunset or sunrise. As the planet turns, different regions move into and out of alignment with the sun. When a location begins to rotate away from direct sunlight, the sun appears to lower in the sky, even though its position in space remains essentially fixed relative to Earth during that short period of time. Sunset is therefore not an event happening in the sky alone, but a moment defined by geometry. The horizon acts as a boundary created by Earth's curvature. As rotation continues, that boundary gradually rises between an observer and the sun, blocking direct light while still allowing scattered light to reach the sky above. The colors of sunset trace this geometric relationship, revealing how light behaves when it must travel longer paths at increasingly shallow angles. What makes sunset especially gentle is the scale of Earth itself. Because the planet is large, rotation occurs at a pace that feels slow to human perception. The sun does not disappear abruptly, but lowers gradually, giving the atmosphere time to reshape the light passing through it. This scale allows motion to become visible without feeling rushed. The sky changes steadily, minute by minute, translating planetary movement into a calm visual experience. The same rotation that produces sunset also governs the regularity of days and nights. No matter where you are on Earth, the sequence repeats predictably. Daylight gives way to evening, twilight fades, and night follows. This consistency exists because Earth's motion is remarkably stable over short timescales. Small variations may occur over thousands or millions of years, but from one evening to the next, rotation remains dependable. At different latitudes, this same motion reveals itself in different ways. Near the equator, rotation carries the sun below the horizon more directly, shortening the visible transition. At higher latitudes, rotation moves the sun along a shallower path, stretching sunset and twilight. In both cases, the underlying cause is identical. Only the angle of Earth's surface relative to the sun changes, altering how motion is experienced from the ground. This planetary motion does not need observation to continue. Earth turns whether or not anyone is watching the sky. Yet sunset offers a rare opportunity to sense that motion without instruments or measurement. The shifting colors, lengthening shadows, and fading brightness provide a visual record of rotation that unfolds slowly enough to be felt rather than calculated. Even the timing of sunset across seasons reflects this same movement combined with Earth's tilt. As the planet orbits the sun, the angle at which rotation presents different regions to sunlight changes. This alters when and where the sun appears to set, but the rotational motion itself remains constant. Sunset adapts in timing and character, while the underlying mechanics continue unchanged. Nothing in this process requires effort, correction, or control. Earth's rotation is not responding to the atmosphere, and the atmosphere is not directing the sun. Each element follows its own physical rules, and sunset emerges naturally where those rules intersect. Motion becomes visible through light, and time becomes visible through color. You don't need to think about rotation or imagine Earth spinning beneath your feet. The sky already carries that information for you. As the sun continues its slow descent, and the horizon gently takes its place between light and darkness, planetary motion expresses itself quietly, transforming steady rotation into a familiar, calming transition from day toward night. As the sun moves farther below the horizon, the sky begins a quieter phase of transition, where color slowly loosens its hold and light thins without resistance. The vivid reds and oranges that define the earlier moments of sunset do not vanish suddenly. Instead, they soften, stretch, and gradually lose intensity as the atmosphere continues to scatter what little sunlight remains along ever longer paths. At this stage, the sun's light no longer reaches the ground directly. Everything visible in the sky comes from scattered light alone, redirected through layers of air far beyond the horizon. Because the remaining light must now travel through an even greater thickness of atmosphere, fewer wavelengths survive the journey intact. Warm tones persist for a time because they scatter less easily, but even these begin to fade as distance increases and intensity diminishes. The sky often shifts toward deeper oranges, muted pinks, and eventually purples during this phase. These colors arise from the blending of remaining warm light with the growing presence of shadow and the first hints of night. Blue light, already widely scattered during the day, begins to dominate the upper sky again, not because more blue light is arriving, but because contrast continues to decrease and brightness levels fall. This gradual fading is strongly influenced by the atmosphere's ability to carry light sideways. Scattered sunlight travels long distances through the air, illuminating the sky well after the sun itself has disappeared. As Earth continues to rotate, that scattered light weakens steadily, thinning like a distant echo rather than stopping abruptly. The process is smooth, continuous, and predictable, shaped by geometry rather than chance. Clouds, if present, often take on darker silhouettes during this phase. Without direct illumination, their edges lose definition and their colors flatten. What once reflected warm tones now absorbs and blocks what little light remains, deepening the contrast between sky and shadow. This change adds depth to the evening sky, not through brightness, but through absence. The human mind responds quietly to this fading. As colors lose intensity, attention naturally shifts away from detail. The sky becomes less something to observe closely and more something to exist beneath. This change does not require thought or interpretation. It happens as perception adjusts to lower light levels, allowing awareness to broaden and soften. Even the pace of fading carries a sense of calm. Because the change unfolds slowly, there is no moment that clearly marks its end. Color thins, then dims, then blends into deeper tones, each step flowing into the next. The lack of sharp boundaries makes the transition feel gentle, as though the sky is letting go rather than being taken over by darkness. You don't need to follow each color as it fades or notice when one shade gives way to another. The atmosphere handles this process quietly, guided by distance and scattering rather than urgency. As the last traces of warm light dissolve into the deepening sky, the fading of color becomes a natural conclusion to the day's visible journey, easing the world softly toward the stillness that follows. As evening continues to deepen, the sky enters a final, quieter phase where light no longer announces itself through color, but lingers gently as presence. This last light of the day is not bright enough to define shapes clearly or paint the horizon in warm tones. Instead, It exists as a soft afterglow, a thin remnant of sunlight still traveling through the atmosphere long after its source has slipped far below the horizon. At this point, all visible light in the sky is scattered light. The sun's rays are no longer reaching the surface directly in any form. What remains has been redirected multiple times through distant layers of air, losing intensity with each interaction. This scattered illumination spreads evenly rather than directionally, creating a sky that feels open and quiet, without a clear focal point. The afterglow often appears as a deepening blue or muted violet overhead, gradually darkening without sharp edges. Near the horizon, faint warmth may persist for a time, but it no longer defines itself clearly as a distinct color. Instead, tones blend together, becoming harder to name. This loss of definition is a natural result of diminishing light levels, where the differences between wavelengths become less pronounced to human perception. The atmosphere continues to play its role even now. High-altitude air still scatters what little sunlight remains, carrying it sideways across vast distances. This is why the sky does not turn dark the moment the sun sets. Earth's atmosphere stretches the end of the day, allowing light to linger softly rather than vanish. The planet's curvature and the thickness of the air work together to slow the arrival of night. As brightness drops further, stars and planets begin to appear more clearly. Their light, traveling directly through space and only briefly through the atmosphere, becomes easier to distinguish against the dimming sky. The contrast between scattered sunlight and distant starlight marks a subtle shift in dominance, where light from beyond Earth begins to replace light filtered by its air. The human mind responds gently to this change. With fewer visual details available, attention relaxes further. The sky becomes less something to examine and more something to rest beneath. The absence of strong color and contrast reduces the need for focus, allowing perception to settle into a quieter, more passive state. Sound and movement often feel different during this time as well. With visual cues fading, the environment may seem more spacious, less crowded by detail. This impression is not caused by silence or stillness arriving suddenly, but by the gradual withdrawal of visual stimulation that once anchored awareness to specific points in space. The last light of the day does not mark a clear boundary. There is no moment that definitively separates twilight from night. Instead, the afterglow thins slowly, becoming harder to notice until it merges seamlessly with darkness. This smooth transition is one of the defining characteristics of Earth's atmosphere, ensuring that night arrives gently rather than abruptly. You don't need to notice when the last light disappears. It fades without announcement, slipping quietly into the background as the sky deepens. The day does not end with a final signal, but with a soft release, as scattered light completes its long journey and allows darkness to take its place, calm and unhurried, across the sky. As the last traces of scattered light continue to thin, the sky reaches a point where color no longer carries the scene forward. What remains is not darkness arriving suddenly, but a gentle settling, where the atmosphere finishes its work and releases what little daylight it has been holding. This moment does not announce itself. It unfolds quietly, almost imperceptibly, as the boundary between twilight and night dissolves. At this stage, the atmosphere is no longer receiving usable sunlight to scatter. The sun sits far enough below the horizon that even the longest atmospheric paths cannot deliver meaningful illumination. Any remaining brightness in the sky comes from sources beyond Earth, stars, planets, and faint reflections of distant light, rather than from the sun itself. The sky transitions from being shaped by filtered daylight to being defined by the absence of it. The colors that once blended so gradually now fade into a uniform depth. Blues deepen, purples darken, and eventually hue gives way to tone alone. The sky becomes less about variation and more about continuity, a broad, uninterrupted field that feels expansive rather than detailed. This change is not abrupt because perception adapts alongside the light, smoothing the transition as contrast diminishes. The human mind responds naturally to this release. With no strong visual signals demanding interpretation, awareness loosens further. The urge to observe fades, replaced by a sense of being held within the environment rather than separate from it. The sky no longer asks to be watched. It simply exists, wide and quiet, offering a backdrop rather than a focus. Physically, nothing dramatic occurs at this moment. Earth continues to rotate at the same steady rate. The atmosphere remains layered and active, even if its effects are no longer visible. Light from the sun continues to travel through space, just no longer intersecting the sky above in a way that produces color or glow. Night is not an event, but a condition that emerges when interaction ends. The stillness that accompanies this phase often feels deeper than silence. Without color or brightness to anchor perception, space itself becomes more noticeable. Distances feel larger, and the sky feels farther away, not because it has moved, but because visual reference points have softened. This expansion contributes to the sense that the day has fully released its hold. Even memory begins to shift during this time. The vivid colors of sunset feel farther away, as though they belong to a different state rather than a different moment. The transition has carried awareness gently from activity to rest, not through instruction, but through gradual withdrawal of stimulation. There is no clear line where sunset ends and night begins. The sky simply lets go, completing a process that began hours earlier with a change in angle and light. The release feels calm because it has been prepared slowly, step, by distance, motion, and time. You don't need to mark this moment or notice its passing. It arrives whether attention is present or not. As the sky settles fully into darkness, the letting go feels complete, leaving behind not absence, but space, quiet, and the sense that the day has closed itself gently, without resistance, allowing night to take over naturally. As darkness settles fully into the sky, nothing new needs to happen. There is no final signal and no last transformation to observe. The atmosphere has completed its work, and light has finished its long, indirect journey. What remains now is not the absence of activity, but a different state entirely, one defined by quiet continuity rather than change. The sky no longer reflects or reshapes sunlight. Instead, it opens into depth. Without scattered light to soften its edges, space feels wider, more expansive. Stars appear steady and distant, their light arriving directly from far beyond Earth, unchanged by the processes that shape the colors of sunset. This shift from filtered daylight to unaltered starlight marks a calm conclusion to the sky's transition. Earth continues to turn, just as it did during the day. The atmosphere continues to move layer by layer, responding to temperature and motion, even if its effects are no longer visible. Nothing has stopped. The rhythms that guided sunsets simply carry on in a quieter form, no longer expressing themselves through color, but through stillness and space. Perception adjusts gently to this new balance. Without bright light or contrast to draw attention outward, awareness turns inward without effort. The world feels less demanding, not because it has gone silent, but because fewer signals compete for focus. Darkness does not remove the environment. It softens it, allowing details to rest rather than disappear. This is why night often feels like a pause rather than an ending. The processes that shape the day remain in motion, but their expressions change. Light gives way to depth, color to tone, motion to steadiness. The transition feels complete because it has been gradual, guided by predictable patterns rather than sudden interruption. There is no need to reflect on what has passed or anticipate what comes next. The sky does not hold on to daylight, and it does not resist darkness. It accepts each state in turn, following the same simple rules it always has. In this acceptance, there is calm. You don't need to observe the night or interpret it. It does not ask for attention. It simply exists, wide and patient, offering a backdrop where thought can slow and awareness can drift without direction. The world feels larger, quieter, and less defined, not because anything has vanished, but because nothing is being emphasized. As Earth carries you further into night, the same steady motion continues beneath you. Somewhere else on the planet, another sunset is beginning, shaped by the same light and air. Here, the cycle rests, complete for now, having moved from brightness to color, from color to stillness, without ever rushing or resisting. You can let the sky remain as it is, dark and open, holding nothing that needs to be followed. The day has released itself fully, and night has taken its place, not as an ending, but as a continuation, quiet and unhurried, allowing everything to settle naturally into rest. Good night.